Alright, so good morning students. Today we will talk about free electron Fermi gas, and the discussion here is basically to complete the topic of heat capacity of a solid at low temperature. So, the motivations are to get an ultimate expression of heat capacity at low temperature, and what I mean by my statement is that, so I know that the heat capacity of a solid is due to lattice vibrations, which is due to vibration of ions about their mean position. So, these vibrations are quantized in terms of phonons. So, we had used a boson theory of solids, and we had derived an expression due to d by, which said that at low temperatures the behavior is T cube. So, let us say that the proportionality constant is alpha. Today we will discuss another contribution to the overall heat capacity of solids at low temperature, and that comes from the free electrons in a metal. So, naturally our discussion is contextually valid only for metals which have free electrons to contribute to the overall heat capacity. So, here at the end of our discussion we will see that this is proportional to temperature at very low values of temperature. So, both the lattice vibrations and free electron contributions saturate to 3 by 2 or saturate to 3 kT in terms of energy at high temperatures. So, the heat capacity at very high temperatures, when neither the lattice vibrations contribute nor the electrons contribute, we see that the heat capacity becomes 3 Nk, which is the Dulong-Petit's law. The exciting stuff only happens at low temperature, where both lattice vibrations and electrons pitch in and contribute to the overall heat capacity. Okay. So, we need to keep this in mind that we have only completed in the first 2 lectures the first half of the heat capacity, which is due to lattice vibrations. Today we will extend the discussion and include the free electrons that are there in any metal, copper for example, iron for example. We shall see how the heat capacity is affected due to free electrons as well. So, that being the introduction, I can start from the statistics of electrons, which are fermions. So, for fermions, I have already discussed that the statistics is due to the Fermi derived statistics, and we can write down the statistics in terms of the occupation number, average occupation number of any jth level as 1 over e to the power beta Ej minus mu plus 1. Okay. And just to keep in mind that this is a Fermi Dirac statistics, I am going to call this as a function of just the energy. Okay. And you can construct the Fermi function especially at 0 temperature, which is basically the limit of infinite beta, as if you look at the Fermi function for all energy values which are less than this chemical potential mu, as beta goes to infinity the exponential turns to 0 because it is e raised to minus infinity. So, for all energy values below the chemical potential, which is called as the Fermi energy at t equal to 0, we have the occupation exactly 1, and it is 0 for all energy values above the Fermi level. So, I am going to call this as the Fermi function or the average occupation number. At t equal to 0 or infinite beta, all energy levels are fully occupied. So, there is no sense of an average occupation level, it is exactly 1 because anyway you have taken an extreme case of t equal to 0. So, what is also indicated in this figure is that I have conveniently taken the chemical potential at t equal to 0 as the Fermi energy. Okay. You can also call this as EF. Okay, if you can call it as EF or MEF, they are the same. Okay. So, just to continue the discussion, I can write down the total number of particles in our system as simply sum over all the average occupation numbers in our Fermi system. Okay. So, that will sum up to the total number of particles in the system. I can also compute the total energy by simply sampling the energy of each level, let us say E j, and sampling in the distribution which is the Fermi Dirac distribution. Okay. So, naturally at t equal to 0, this would simply be sum over all the energies from 0 to Fermi level, and the excitation of each level is just 1. It would be nothing but number of fermions that are there in the system times their energies. So, these definitions that I have written is precisely valid at all t. So, which means they are applicable at all temperatures, not just at t equal to 0. Because if you take temperature at t equal to 0, then Nj strictly becomes 1 and it comes outside the summation. You simply sum over all Ej's to get the total energy of the system. Okay. As you can see from this figure that our Fermi Dirac statistics is exactly 1 for at t equal to 0 for all energy values below the Fermi surface. Now, we are looking in general systems where the number of particles usually is a very large number. For example, we are dealing with metal objects in our laboratory experiments, or we are dealing with solids where n is of the order of 10 to the power 23. It is a very large number, and of course, the volumes are very large. Okay, the volumes are millimeter cube or centimeter cube compared to the volume occupied by an atom or a molecule. This is a very large volume. So, the numbers themselves are very large, and but we have a finite density. So, this limit of the extensive variables n and v being very large such that the intensive variable density becomes finite is called as a thermodynamic limit. So, we are working in thermodynamic limit. Where these two extensive quantities n and v are so large that the energy levels become almost a continuum, and the spacing between, and that is because you are stacking too many modes in the energy spectrum, that the separation between modes essentially goes to 0 as number of particles in volume go to infinity. For example, if you look at a typical electron in a box, we are having many electrons in the box. So, let us look at just one electron in a box. The meaning of thermodynamic limit becomes very clear here. So, this is a standard electron in a box problem that you have seen in your quantum mechanics introductions. If you have not, but then I am going to assume that you already know a little bit about particle in a box. So, I have taken a box of length L. So, I am going to take it as a the box length to be the walls at 0 and L, and this is going to be my x axis, and this is basically a infinite well, in the sense that my potential energy outside the box is infinite and it is 0 inside, 0 or any constant value. After all, it is the gradient or the change in potential energy that translates into a force. The reference values of the potential energy themselves do not really it is just an additive constant in the overall energy of the system. So, the infinity potential here only implies that the particle is never allowed to escape from the box. It is like if you imagine a conductor of length L, I would never expect the electrons in the conductor to leave the conductor. So, the conductor's length here is the L here. Okay. Now, you can think of the electron as a wave that is in some sense a solution of a Schrodinger equation. So, you can think of the wave like solutions as psi of x as some normalization constant into sine of n pi x by L. You will do it for many electrons. Right now, I am showing it for just one electron, and so naturally this would be the case for n equals to 1. You can consider higher n's, okay, for n equal to 2, you can consider another case such as, right. So, now if I write down the wave function like this, it is immediately clear that the allowed wave vectors that I have assumed are basically, well, this was a 1D case. So, in 3 dimension it would be a product of 3 sine functions, and I can write down my wave vector as a triplet of kx, ky and kz, which essentially means that I can write down this as a triplet of the excitation numbers nx, ny and nz times pi by L. So, that would be my k in 3 dimensions. Now, these values of k, kx, ky and kz, which are due to the excitations nx, ny and nz, they actually are always positive. The simple reason being that if I take negative values of these excitations, it does nothing to my wave function except for except that it incurs an overall negative sign in my wave function, which does not pose any problem, because at the end of the day I will be looking only at the expectation value, which is required for which the probability density is required, and that is mod psi star. And so, the negative values of the wave functions pose no bearing on the expectation value of observables in quantum mechanics. So, I am going to take only positive values of these excitations. Negative values affect the system in no way, except that the overall wave function becomes negative, and we are not interested in negative excitations precisely for that matter. Now, so I can now write down, if you can see now, as the system size, which is L, goes to infinity, that is my volume goes to infinity, these become very closely stacked. Okay. Right, because as L goes to infinity, the spacing between them, which goes as 1 upon L in some sense, becomes very very small, and so the energy spectrum becomes almost a continuous spectrum, which means that my summation over all the modes have to now be replaced as n and volume both go to infinity by an integral over modes. And naturally, when I replace the summation by an integral, I need to account for a certain density of states, which in some sense is a number of states per unit mode number, okay. Because dimensionally Gk has to have dimensions of 1 upon k, so that the integral becomes dimensionless. So, that is the effect of increasing a system size to infinity, that you naturally get the concept of a density of states. Now, to compute density of states, you can imagine your K space as basically an octant where kx, ky and kz are positive, for the reason that we have just mentioned, that we are interested only in positive values of the excitations. The negative values have no bearing on the overall observables. So, I can think of one octant in my K space, the so called the octant where all values of my components of the wave vector k are positive. So, I can take one on this surface, I can take some value of my k, which is given as the set of 3 components all greater than 0, and now I can just compute the number of states inside this octant. Okay. So, if I was going to compute the number of states in an entire sphere of radius k, I would get precisely 8 times the number of modes that I need for my calculation, okay. But I do not want that, which means when I write down for the number of modes, let us say dn in some arbitrary volume element, this would be nothing but the volume of this volume element, that is d cube k, over the minimum volume one can imagine inside this k space. The minimum volume is due to the minimum k values, okay. And naturally this has to be multiplied to the degeneracy of the fermions, because each fermion has a spin half, and that gives it in some sense 2 polarizations for any value of k. So, it can be in in 2 states, s being half. So, 2s plus 1 is the degeneracy. So, it can be plus 1 or minus 1 states, and you have to also account for the fact that we are only interested in the octant where kx, ky and kz are positive. If you do not take into consideration that, you would be overcounting the number of states by a factor of 8. So, precisely to account for that positiveness of the excitations nx, ny and nz, I have taken the factor of 1 by 8. So, this is basically to remind us that we are taking only nx, y and nz as positive, okay. So, now we can write down dn modes in volume element d cube k as, I can write down the volume element as 4 pi k square into dk, 4 pi k square here being the surface area of the sphere at radius k, and dk is a small shell at the radius k. So, the volume of the spherical shell is 4 pi k square dk multiplied by of course, our degeneracy factor into the fact that I am going to be interested only in the positive values of the excitation. So, hence only 1/8 of the total volume is going to be constructed, is going to be used, and I am going to divide it by the minimum volume, and that is constructed by simply taking the minimum k. Now, the minimum k here is if you take nx, ny and nz as 1, the minimum k comes out to be just pi by L. Okay. So, along the x direction the minimum k is pi by L, along the y direction it is pi by L, and along the z direction it is pi by L, corresponding to nx, ny and nz taken as 1. So, I am going to take pi by L and raise it to power 3. So, then this will give me, if I take all the prefactors in one place, I would be getting 2s plus 1 into k square into volume dk over 2 pi square. 4 times 2 is 8, and we have a pi cube in the denominator and a pi in the numerator. I think I have taken care of all the factors. Okay. So, now this is my g of k into dk. So, this is basically giving us the density of states in the k space. So, my g of k is now 2s plus 1 into volume into k square over 2 pi square. Okay. So, then I can compute a few important quantities. So, let us compute first n, the total number of particles. So, n is nothing but integral density of states into k. So, basically this quantity, if you recall, is nothing but number of particles per unit k space. So, if you integrate this density over the entire k space, then you should recover the total number of particles, as long as you take the limits on the integral from 0 to the Fermi wave number, because we are integrating it at t equal to 0. I expect all my electrons to be within the Fermi sphere. So, the upper limit of my integral is Fermi wave vector, and this will give me the total number of particles to be as n. So, at t equal to 0, if I do this integration, I will recover the number of particles, and that would give me the definition of the Fermi wave vector. Let us do that integral. We will simply substitute g k from up above, and that would become 2s plus 1 over 2 pi square into v, and integration on k square will simply become kf cube by 3. So, you can recast this equation in terms of the Fermi wave vector as simply 6 pi square over 2s plus 1 into n by v, the whole thing raised to power 1/3. Okay. So, this is my Fermi wave vector. I can also compute now because I have the Fermi wave vector with me, I can compute my Fermi energy. So, computing Fermi energy, I can use this expression of the energy h cut square k f square over 2 m, okay. And this will give me the Fermi energy as nothing but I just have to multiply h cut square by 2 m to the above obtained expression for Fermi energy, Fermi wave vector. So, this would be just 6 pi square over 2 s plus 1 into n by v raised to the power 2/3. Okay. And let us compute one more quantity, which is Fermi temperature. Now, since we have an energy scale, I can always compute a temperature commensurate with that energy scale. So, the Fermi temperature I can compute by simply saying that this is of the order of the Fermi energy over the Boltzmann constant. Okay. So, this would be nothing but h cut square over twice m the Boltzmann constant into 6 pi square over 2 s plus 1 into n over v raised to 2/3. Okay. Now, let us get a feeling of these numbers. So, you can just to get a feel of these numbers, which is important because see they are the consequence of our system being treated quantum mechanically. So, the consequence of treating electrons as a system of fermions which obey Pauli's exclusion principle, and the fact that we are squeezing so many of them in a small volume, in a volume which is pushing your densities to 10 to the power 28 per meter cube for typical metals like copper, has natural consequences on these values, and you should see the strength of these numbers to sort of have an appreciation of the quantum mechanics that goes into the calculation. Okay. So, take for example copper, and which is an extremely good conductor. So, the number density of copper is roughly number density of electrons is usually 10 to the power 28 per meter cube. Okay. And just to get a feel of these numbers for a typical metal, the numbers will not vary much. So, it will give you an order of magnitude estimate. So, let us compute for example, the Fermi wave vector's magnitude. This would be of the order of the density to the power 1/3, and that is nothing but roughly, if I take 10 to the 28 and raise 1/3 of it, it is roughly 10 to the power 9 per meter. Okay. And so, the wavelength will be typically a nanometer, because k is inverse of the wavelength. And if you want to get a feel for the Fermi energy, this would be, if you look at the expression of Fermi energy on the left, I have a Planck constant to the power 2. So, that is giving me a 10 to the minus 68. I have an electron mass in the denominator, that is giving me 10 to the power minus 31, which when taken upstairs becomes 10 to the power 31, and I have the density to the power 2/3. Density to the power 1/3 is already 10 to the power 9. If I raise it to the power 2, it becomes 18, and this would be in joules. So, if you sum up all the terms, this becomes roughly 10 to the power minus 19 joules, which is like an electron volt. So, the Fermi energy comes out to be of the order of an electron volt. Now, just to give an example, just to give you a feel, an electron volt is a very high energy scale, because if you compute the temperature corresponding to an electron volt, it will come out to be a very large number. Okay. So, the Fermi temperature which corresponds to an energy of the order of an electron volt, comes out to be, I will take an electron volt which is 10 to the power minus 19 joules and divide it by the Boltzmann constant, which is roughly, I am going to just take the Boltzmann constant upstairs. So, this would just give me 10 to the power 23, and so that is in Kelvin, and it will come out to be around 10 to the power 4 Kelvin. So, about 10,000 Kelvin is the temperature of the Fermi surface, whose energy is around electron volt. So, this immediately tells me something, that at room temperature the ratio of if I take the room temperature with 300 Kelvin, which is not a, which is a decent approximation, the ratio of T over Tf is going to be a very small number, and it tells me that for most purposes room temperature is considered to be a classical regime, because the corrections that are going to be done over and above the Dulong-Petit's law are of the order of T by Tf. So, they have become very, very small as temperatures are equal or above the room temperature, where you always see the heat capacity becoming independent of temperature, become just 3 kb, 3 times n kb. So, this ratio of n T over Tf will be shown that it is related to the fraction of the fermions excited at room temperature fraction of excited electrons at any temperature, which is taken to be the room temperature in this case. So, roughly T over Tf fraction of the total number of electrons will contribute to the heat capacity. Now, this is a very small number. So, it is enough to have a very small fraction of the electrons of the total 10 to the power 28 in your if you take a meter cube sample, then out of these 10 to the power 28 only about T over Tf, which is a number that is very, very small, that is just 1 upon 100, okay, if you are taking temperature to be room temperature, contributing to your overall heat capacity. So, let us now compute the density of states in terms of energy. So, what we have computed so far is g of k, and this was computed to be 2s plus 1 V k square upon 2 pi square into d of k, and if you to get the density of states in terms of energy. Okay, so, I am going to call this as let me use a different symbol for density of states in terms of energy. So, let me call density of states for energy as rho in terms of energy. That means I am looking for density of states which will give me number of states per unit energy interval. Okay. So, I can compute this by equating it to rho e dE because after all whether I compute the density in k space or energy space, the conservation of the number of particles says that I must get the same number of particles whether I integrate the density in k space or density in energy space. Okay. I am going to use the symbol rho e. Okay. So, then if I look at the expression here, I am going to call this as equation 2. Call this as equation 1. So, I can use equation 2 and write down for my g of k, which is basically g of k dk as simply 2s plus 1 into v k square over 2 pi square dk, and simply using the fact that the energy is related to the wave vector as h cut square k square by 2 m. So, this gives me k square as nothing but twice m e over h cut square, and it can give me dk as 1 upon k m e over h cut square. Okay. So, I can write for dk as h cut square over 2 m e to the power half, okay, into m e by h cut square. Fine. Of course, there has to be this will be m times d e. Okay. Fine, because if I take a derivative with respect to k, I get 2 k dk equals to 2 m d e by h cut square. The factor of 2 cancels from both sides, and now I can write this as so therefore, I can write down my density of states as g of k dk as 2s plus 1 into v times k square, which is twice m e over h cut square, and dk has already been written as h cut square over twice m e raised to half into m by h cut square d e. Fine. Okay. So, then I can write down the density of states as 2s plus 1 into V into Vm over 2 pi square h cut square into twice me over h cut square to the power half dE. Okay. You can take the e raised to half outside. To show that the density of states, and this is nothing but your density of states in terms of energy. Okay. So, our density of states now in terms of energy is 2s plus 1 into V m by 2 pi square h cut square into 2 m by h cut square raised to half into e raised to half dE. Okay. Yeah. So, then let us check if everything is fine. So, our E was defined as h cut square k square by 2 m, and now you have defined it like this. So, I have substitute for k square as twice me by h cut square, and substitute for dk as 1 upon k. I can also simplify this expression. Let us call this as equation 3. So, if you use this expression of the Fermi energy, you can actually write down a simpler expression. So, you can use this expression of Fermi energy. So, you recall that your Fermi energy was given by this expression. So, I can compute for